Hi, everyone, and welcome to your last week of recorded video lectures for this class. Next week, Monday, Tuesday, of course, as we're wrapping up the semester, is when you'll have an opportunity to take test 3 for this class. But this week, we'll be digging a little deeper, still continuing with the content in chapter 15. Hopefully, after last week's second class, you've developed a little bit of a feeling for what is going on in the world of hypothesis testing. But today we're going to do a few more examples, break it down in a step-by-step way so that you can have a methodological way of approaching this, that you can outline for yourself. Step 1, make sure I've done this. Step 2, make sure I've done the next thing. So let's jump in. Your first step is always going to be making sure that you have formulated and clearly stated what your hypotheses are. So there will always be a null hypothesis, which we denote H with a subscript 0, and there will always be an alternative hypothesis, which we denote A, H with a subscript A. Now, the null hypothesis is the hypothesis that maintains the status quo. It's telling us something has been established in the past, it's always been a specific way, and it will continue being that way. That's the way our null hypothesis reads. It's just telling us that there is nothing new or nothing different that's going on. And so because of that, you're often trying to disprove the null hypothesis. But mathematically, it's required that we have this equality statement for our null hypothesis. So what that's typically going to look like is you're going to, under the null hypothesis, say that the parameter of interest is equal to some hypothesized value. The hypothesized value, that's where the status quo is represented. So whatever value had previously been established, that is typically going to be the hypothesized value. And then the parameter, remember that that is a quantity that is relevant to the population. So the goal always here is to make a statement about the population. That's what the test is about. But the reason we have to do the testing is because we cannot observe every single person or every single object in a population. We can only take a sample. So the hypothesis test is that link between what can we say about the population based on information in our sample. So null hypothesis says nothing has changed. The population parameter is still equal to the hypothesized value. The alternative is where we acknowledge that something has changed. Now, that can take on several different forms. We can talk about something just having generically changed, and that will typically be represented by a not equal sign. So that's not telling you that something has shifted in a particular direction. It is just saying it is no longer the same as the status quo. Something is different now. But under this alternative, you don't have information about how that change may have occurred. Of course, the other option here is you'll often have an alternative that acknowledges, oh, something may have gotten bigger or smaller. There may have been an increase, which corresponds to saying that the parameter is now greater than the hypothesized value. Or there may have been a decrease, which says, okay, now the parameter is less than the hypothesized value. So you have to clearly read what the problem setup says and what the goal of the research is. It will often be acknowledged in there how your alternative is formulated. And the alternative hypothesis formulation becomes really important later on when we're doing the final calculations for our hypothesis test. But step 1 will always be formulating null and alternative hypotheses. So let's look at an example of that. Let's say that the DMV claims that 80% of all drivers pass the test the first time. So this claim represents the status quo, right? That's just what they say has always been going on. 80% of people pass the driver test. But then they do a survey. They take 90 randomly selected teams out of all teams who take the test and find that 61 of them passed. And they want to determine whether there is evidence that the teen pass rate is now below 80%. So that is an alternative that suggests there is a decrease, right, below 80%. So our null hypothesis will maintain the status quo. In this case, we're dealing with a percentage or a proportion. And remember that the notation for that is P. So we're saying that the proportion P under the null hypothesis is still equal to 80%, but under the alternative, the proportion is now less than 80%. And there you have it, a null and an alternative hypothesis. This should be the least complicated part of the testing procedure. Next, you're going to figure out which model is appropriate, because the model will have conditions that need to be checked. And if those conditions, for whatever reason, are not satisfied, that means you can't continue with the test. If this was a big study being planned, people would have to know, okay, the study, the way we've designed it won't work because our model is not going to meet the conditions and we won't be able to use the appropriate test. The model that we'll see a whole lot in our examples is the normal model. And the normal model is based on z-scores. Other models use different quantities. Now, in the example that we were just talking about, we are looking at a proportion, and a test for a proportion ends up being based on a z-score. So in that example, we're looking at a one proportion z-test. Now, what are the conditions here? There is a parallel here between the conditions for a testing problem and the conditions for a confidence interval problem. So you want to make sure you go and review under which conditions you can construct a confidence interval for a proportion, because you need those same conditions to be true for the testing problem. Now, if those conditions are satisfied, then you are going to calculate a test statistic. And for the one proportion z-test, your test statistic is going to be p hat, remember that's your sample proportion, minus p0, that's the value under the null hypothesis. And then we always divide by a standard error, and in this case I'm denoting it SE with a subscript 0, because this is calculated specifically for this hypothesis testing problem. So if you're dealing with a proportion, let me emphasize this here. If you're dealing with a proportion, then the way you're going to calculate the standard error is the square root of P0 times Q0 over N. So it should look somewhat familiar. You've seen a similar standard error formula before, but it is calculated assuming the null hypothesis is true, which is why we use the value P0 and not the value P hat. Now, in this example, let's also run through the conditions that you want to check. So when we're talking about a proportion test or a proportion confidence interval, first condition is randomization. In this case, we are told that the teens are a random sample. And specifically, if we want to make a statement about teens in general, then the sample needs to be of teens taking the driver test. Like the sample has to be representative. that's why the randomization is so important. Next, we have the 10% condition. Remember, our sample size cannot exceed 10% of the population. Now, how many teens take a driving test in the US every year? Hundreds of thousands. And so 90 people in the sample is definitely well below the 10% threshold of the entire population. Then we have the success-failure conditions. And again, you'll note here, these are now calculated using P0 and Q0. So it'll be your sample size multiplied by the proportion under the null hypothesis. And the sample size times the complement of that proportion. And if you do these calculations, in both cases, the quantity is at least 10, which means success-failure condition is satisfied. So in this case, conditions are satisfied, and that means we can use the normal model for this proportions test. Your third step after checking the conditions will be to calculate the appropriate test statistic and p-value. So we wrote down the formula for our test statistic a moment ago. It was the z-test. To calculate that, we need to know the value of p hat, our sample proportion. Now in this case, that's 61 over 90. That was our sample or our empirical pass rate. And if you calculate this, you'll get 0.678. The other quantity we need here is the SE0, the standard error calculated assuming the null hypothesis is true. So in this case, it'll be 0.8 times 0.2 divided by your sample size of 90 and square root of that entire quantity. And if you calculate this, you'll get 0.042. So this now allows us to calculate our z-test, the p hat minus p naught over SE naught, which in this case is 0.678 minus 0.8 divided by 0.042. And that ends up being very close to negative 2.9. Now, this is where the importance of the alternative hypothesis comes in. Our alternative hypothesis here is that P is now less than 80%. The less than 80% tells us which part of the bell curve we're interested in. So we have a standard bell curve centered at 0. We've calculated this z value of negative 2.9. That's our reference value. And because the P is less than that value, the less than tells us that we want to know what the normal value is for the bell curve to the left of negative 2.9. Remember, this is what you can look up directly in your Z table. And if you look up negative 2.9, the Z table is going to give you 0.002. So that is our p-value in this case. P-value is 0.002. What do we do with that? We have to reach a conclusion. Your final step in hypothesis testing is writing down a conclusion based on what you are seeing. So in this case, is the teen pass rate still reasonably assumed to be 80%, or is it now less than 80%? Well, because the p-value is very small, we are going to reject the null hypothesis. So the data we've collected provides evidence that the null hypothesis is not true, which means the pass rate is no longer 80%. And under the alternative, that means we reasonably assume now that it is less than 80%. So that has to be your conclusion. Your conclusion has to be, in this case, because you reject the null hypothesis, it has to be a statement consistent with the alternative. But this should never be the end of the conversation. There always should be a recommendation of a follow-up study, because since we are only working with a sample and not with the entire population, there's always the possibility that we reached a wrong conclusion. And so follow-up study to determine whether we reached a good decision or not, confirmation of what we found, but also real-world application. Like, what does it mean for the DMV if the pass rate has dropped below 80%? They need to formulate a plan of action around that. Is this a good or a bad thing? Like, it doesn't have to be a bad thing, but it could be reflective of driver training. It could be reflective of a need for them to have more testing capacity. There are many different things that could be practical for them to implement if they find that this change has occurred. So just reaching a conclusion should never be where you stop. Now, we just worked through an example looking at a proportion, and I did mention last week there are just two types of hypothesis tests that we will be concerned with here. Tests dealing with proportions and tests dealing with means. So we're going to walk through one more example here of a test dealing with a mean, but one in which we have to take a little bit of extra care. So the one sample t-test is the test that is appropriate to use if certain conditions are met. Those being, we have a population that is normal or nearly so. And secondly, we're having to use standard error, not standard deviation. And the reason for that generally is sigma, our population standard deviation, is not known. And so we use S, our sample standard deviation. So in this case, our null hypothesis will be that the population mean, mu, is equal to some hypothesized value. And the alternative can take the three forms we've discussed previously: not equal to, less than, greater than. You have to determine from the context which is appropriate to your setting. Now, if you've determined that you're in the t-test framework, so normal or a nearly normal model, but the population standard deviation is unknown, then your test statistic will be the t-statistic, defined as y bar minus mu 0 over the standard error of y bar, and the standard error of y bar, or the standard error of our sample average, is equal to the sample standard deviation over the square root of n. And this quantity uses a student's t-model with n-1 degrees of freedom. So that's what we will use to calculate the p-value for this test. So we have some data on hand looking at farmed salmon, and the EPA recommends that salmon should never have Merex levels that exceed a threshold of 0.08 parts per million. So of the farmed salmon operations, a sample is taken, 150 salmon, and in the sample, the average Merex level is 0.0913 parts per million. And the sample standard deviation is 0.0495 parts per million. So here, we are concerned about the level being above the EPA threshold. So our null hypothesis will always be the status quo, or in this case, that means the recommended value. Our null hypothesis says the truth is consistent with the recommendation. And the alternative says, no, we are exceeding that recommendation. That's what we are concerned about. We don't want to be above this level, so that's what we formulate as our alternative. How do we calculate our test here? Well, we first have to figure out our standard error. Standard error for the sample average is sample standard deviation S over square root of n, which in this case is 0.0495 over the square root of 150, and that is very close to 0.004. This now allows us to calculate our t-statistic. Remember, y bar minus mu 0 over the standard error of y bar, which in this case means we're taking our sample average, subtracting the null hypothesis value, and then dividing by the standard error that we just calculated, and this gives us a value of 2.825. Now, for the p-value, we now have to use a t-distribution as a reference. Now remember, that still follows a bell curve. So I'm drawing a bell curve, but in this case, it represents a t-distribution with 149 degrees of freedom, one less than the sample size. We calculate a value of 2.825. And in this case, our alternative was that we exceed the threshold greater than. So in this case, our p-value is the bell curve region to the right of our test statistic. Now, one of the tricks here is when your degrees of freedom are large, and large is typically a number beyond 50, the t and the z distributions are really, really close. So in this case, I can calculate the p-value kind of almost using the trick of using my z distribution. And if I look up the area to the left, I will find that is 0.9946. That's what the z table will give me. And so the p-value will be the area to the right, 1 minus that area to the left, and in this case, that is 0.0054. Again, this is a small p-value. This p-value is 0.5%. And so because the p-value is small, we are again going to reject our null hypothesis. So we have to state a conclusion. Our conclusion in this case has to be consistent with the alternative. And that would be that the average Mirex level in the salmon population appears to exceed the EPA recommendation. And that's a problem, right? That means the salmon arriving at your door, if it's not wild-caught salmon, if it's farmed salmon, it has high levels of a pollutant in it, which could be dangerous to your health. So again, two things should happen. Firstly, someone should probably do a confirmatory study, go and collect independent data, run the same kind of test. But on the other side, we should practically think through what it means if these Mirex levels are higher than what the EPA recommends. Is the EPA guideline outdated? Should that be revisited? Is it really dangerous to have higher Mirex levels in salmon? And if so, farming practices should be addressed. So there should always be this twofold follow-up of doing a confirmatory analysis and figuring out what the implications are in a specific setting. So we will work through a few more examples during our next live Zoom session, but I hope all of you have had a good start to your week, and I will talk to you soon.